This should look familiar. What kind of function is this, y'all? If you saw this in algebra, what kind of function is it? Yeah, quadratic, right? It's a quadratic function. Okay, so this is a quadratic function. What do you know about quadratic functions? Well, they're U-shaped, right? You know it's going to have some kind of, if you went to write your function, it'd be in this format. Yeah, there's an x squared. And chapter 4 is all going to be about analyzing graphs of functions, analyzing derivatives from the graph of the function, analyzing stuff about a function from a graph of a derivative, being given a graph of a function and creating a graph of the derivative, being given a derivative graph and creating a function graph. It's graphs, graphs, graphs. So just curious from algebra, what are some important points on this parabola that y'all talked about in your algebra course? So you can just put an ordered pair in the chat. What is an important ordered pair on this graph? Okay, so so one important ordered pair there, Emma says, is where the function equals 0. Totally agree. Oh, flip-flopped it. Yeah, that's okay. So let's put it out. So where the function equals 0, right here. This is an important point right here. This point, 1 comma 0, that means if I put 1 into the function, if I input 1, so my x is a 1, I'm going to output a 0. That's an important point on the function. It's called the zeros of the function from your algebra class. So same thing over here for this point, right? So also, if x is a 3, my output is a 0. So we write that as f of 3 equals 0. Those are important points. Those are called the zeros of the function. So I'm going to say that x equals 1 and x equals 3 are the zeros. They call them the zeros of the function. And they're also called what? Instead of zeros, what's another name that we can call those? What kind of intercept? Yeah, the x-intercepts, right? So these are also called your x-intercepts. So x-intercepts are important. Patrick pointed out another important point. So let me mark it on here. This point right here. So 2 comma negative 1. Okay, do you remember what special name this point has? Oh, sorry, it was Priscilla that pointed it out. Yeah, the vertex, right? That's the vertex. So this is the vertex of the parabola. Vertex, but it's also called the local minimum. Go to your status and show me a status if you remember the term minimum or local minimum from your previous class. So go to your status. Do you remember talking about local mins, local maxes, absolute mins, absolute maxes? Okay, so most of y'all are kind of dusting some cobwebs off. A couple of y'all not. That's okay. We'll cover it again. I just wanted to remind us, you know stuff about graphs, and none of this is calculus that we're doing right now, right? This is just algebra. We're going to connect it to calculus, but right now it's just algebra. Okay, so that's a local min, and again, you can write any ordered pair in function notation. If I put a 2 into this function, I get a negative 1 out, and that means, what does this mean? That means negative 1 is the lowest output. Is the lowest output, right? So when you're talking about minimums of a function, you want to know how low does that output go. Okay, so those are all important parts of functions. So now I'm going to change back to the notes, and we're going to just see what all the notation for this looks like. Like what kind of questions could you be asked to analyze this original function graph, okay? So I'm going to pull the notes back up. It's the same graph. We're just going to translate these ideas onto the notes. Okay, so let me share the notes now. See, y'all know more than you think about graphs. People always get freaked out with graphs, but I promise you have the foundation in there somewhere. You just might have to dust more cobwebs off than we'd like. Okay, cool. So these are the notes. Let me make sure they're sharing. Okay, it is not sharing. Give me 1 second. Application, notes, go. There it goes. Okay. So on your notes, if you printed them out, the first page is just a whole bunch of definitions, things I'm going to be talking about, things for you to read through. This chapter, we're going to bring this idea of second derivatives around. I just have a whole bunch of things to remember. So I'm going to be talking about this. I just wanted to put it in writing so when you're studying, you can refer to it. But these are all things I'm going to say verbally later. So I want to start on this page right here. This is the graph we just saw, and we're just going to formalize everything that we talked about. So now I've given us the equation, so I can see from the function it's quadratic. I can see from the shape that it's quadratic. One question you could be asked is, for what values of x does the function equal 0? And y'all already told me that those are the x-intercepts, right? So when x equals 1 and x equals 3, if I put a 1 into the function, I get a 0 out. If I put a 3 into the function, I get a 0 out. So remember to read your function notation to help you with these. It's asking, what would I input into the function to get an output of 0? So I know what the output is, and the outputs are the heights of the graph, right? So outputs are always heights of graphs. Height of graph. And if your height is 0, you're right there on the x-axis. Okay. And for what values of x do we have a minimum? So if they're just asking me for the values of x, that would be when x equals 2, right? When x equals 2, that was my minimum. Okay. So for what values of x does it have a minimum? So make sure you're reading really carefully on MyMathLab. Now, what is the minimum? I would say the minimum value is -1, but it happens when x equals 2. Okay, so those are the points that y'all picked out on the graph. Now let's look at C. What is C asking us here? C says, over what x interval is f of x less than 0? What is that asking us? For over what x interval is f of x less than 0? What is that asking us? I heard a little chime. Does someone have? Ooh, okay. So Emma has a suggestion. There's from -infinity to 3. Okay, and I think I see where you're going with that. And then there's some suggestions from 1 to 3. So 3, y'all are all agreeing on the 3. Okay, cool. So let's look at this 3 here. I agree with this 3. So when I go to look at this notation, let's interpret it. What does f of x even mean? F of x is an output, y'all. It's what you get when you plug x into the function. So f of x, this stands for the outputs we get when we plug x's into the function, right? And if we want that output to be less than 0, okay, the whole y-axis are my outputs. All of this axis are my outputs. Some of those outputs are positive and some of them are negative. So the negative outputs are down here. This is where your function, your outputs are going to be less than 0. Less than 0 means negative. So your function is going to have negative outputs in this entire region, and that's happening from when my input is 1 until my input is 3. We don't include the 1 because at 1 it actually equals 0, right? So I'm going to put a parenthesis there. And I don't include the 3 because at 3 it actually equals 0. So I put a parenthesis. If it was negative, I do a bracket. Or if it said less than or equal to 0, I would include a bracket, but it just says strictly less than, so I'm just going to put a parenthesis there. That's where my function values are negative. So let me pause there. Show me a status. How are you feeling now that we dusted some cobwebs off on the outputs being less than 0 or the outputs being negative between 1 and 3? So it's all about reading function notation. You have to remember when you see f of x, that's representing an output. It's representing what you get when you put x into a function. When you put an input into a function, you calculate an output. So you just got to keep that in mind, okay? So let's look at the reverse of that now. Now we're being asked over what x interval is the function going to be greater than 0, or the output's going to be greater than 0, right? Greater than 0 just means positive. So this is asking where are the outputs? Where are outputs positive? Well, they're positive if they're above the x-axis, right? So that's going to be above x-axis. Maybe I should go up here for C and put below x-axis. Okay, so above the x-axis, here and here, that's where my outputs are positive. And again, at 1, it's equal to 0, so I'm not going to include that. And at 3, it's also equal to 0, so I'm not going to include that one either. Oops. Okay. Sorry about that. Okay, so how would we write that? We would write it this way. I'm going to go from negative infinity. So any of these x's, if x is 0, for example, if x is 0 when I come up here, f of 0 is going to be 3. See how that's a positive output? Right? And if I did negative 1 and I come up here, my graph would be way up there, but it would definitely be positive, right? And if I did negative 20, I'd be up high. And if I did negative 30, I'd be up high. So negative infinity all the way up till I hit 1, not included. Then I have to hop over the negative region and I pick back up at 3. From 3 all the way to infinity, it's going to be, oops, I put that in the wrong spot. Let me switch this over here. Give me 1 second. Sorry, y'all. So this is going to be where the outputs were negative. This is going to be where my outputs are positive. Okay, so I put that answer in the wrong spot. Okay, show me a status. How do you feel about that idea of positive outputs? Are you feeling any better? Show me a status. Okay. Got a couple more happy faces. It's starting to sink in, maybe. Remember, the real learning doesn't happen here in the classroom. I only see you for an hour, 20 minutes, and we only do math for like an hour of that. So the real learning happens outside the classroom. Okay, now here's some more terms from algebra. Remember, we haven't done any calculus yet. Let's look at this term right here. Where over what x intervals is f of x decreasing? Remember, f of x is an output. Where are the outputs decreasing? I'll give you a second just to jot down where you think, and then we'll talk about it. Ooh, I heard a little chat. There. Okay. Oh, yep, you're right. Okay. Okay, yeah. So decreasing means if your outputs are decreasing, that means the y values are going down, right? So for example, at 0, I was up here at an output of 3. Then at, let's do, what is this, like 1/2? At 1/2, my output was like at 1.5. And then at 1, my output was 0. And then at 1.5, my output was down here. See how my outputs went from 3 to 1.5 to 0 to negative 1/2. Like my outputs are going down in that whole region until they hit my minimum. So all along that interval from negative infinity all the way till we get to 2, my outputs, my y values are decreasing, decreasing, decreasing. And then on the flip side of that, where would the outputs be increasing? On the other side, right? My output's way down here at -1. So I start at -1, and then my outputs are getting higher and higher. Now they're at 0, now they're at 1, now they're at 2, now they're at 3, now my output's 4. all along here, my outputs are going up. So outputs are increasing from 2, not included. Now, at the minimum, you're neither increasing or decreasing. 0 is neither negative or positive, right? It's just there, but all the way till infinity. Okay, so give me a status to show me how you're feeling on these ideas of outputs f of x decreasing and outputs increasing. Because all of these are going to get connected to derivatives in a minute. So I have to make sure you understand the algebra before we can jump into the calculus. Okay, algebra review over. We're going to start connecting it to calculus. Here we go. Okay, so now let's look at what H is asking us. H is asking for what values of x does f prime equal to 0. F prime is the derivative. The derivative is the slope of the tangent line. We learned that back on test 1, right? So for what value of x would the derivative be 0? You can drop it in the chat. Any ideas? On this parabola, where would the slope of the tangent line hit 0? That's right, Cassandra, at the minimum. So down here, if I look at my minimum and I think about a line tangent to that point, see how it's a horizontal line and horizontal lines have a slope of 0? So at that minimum value, I would say the actual function is -1, but the derivative at that point is 0. So reading this notation is going to be critical in this chapter. If I say f of 2, that's just a point on the graph. But if I say f prime of 2, we're describing the slope of the tangent line at that point on the graph. So for what x value does the derivative equal 0? When x equals 2. So slow your brain down, read the notation. What about I here? I says, over what x interval is the derivative this time, derivative less than 0 means negative. Where would your derivative be negative? That's saying where are the slopes of the tangent lines negative? Where are the slopes of the tangent lines negative? Yeah, when we're less than 2, right? So the minimum is separating the decreasing from the increasing. Remember, derivatives are rates of change. So if I'm not thinking about a graph, I can think about a derivative as a rate of change. That's what we did on test 2. And if a derivative is negative, that means your profit or your revenue or whatever was decreasing, right? It was going down. So if my derivative is describing the function and my derivative is negative, it's telling me that the rate of change of my original function is decreasing. It's going down. So actually, E and I are talking about the same thing. If my function is decreasing, the rate of change should be negative. If the rate of change is negative, my tangent lines would be negative. My derivative would be negative. So everywhere in this region, till I hit my minimum, I'm going to have a negative tangent line. So I'm going to write that as from negative infinity all the way till I hit 2. Or you could just say for x values less than 2. That would work also. Or you could say anywhere to the left of the minimum on this graph. But the notation here with the interval notation is what my MATLAB's going to want. So make sure you're really fluent with that interval notation. Okay, so now that we talked about that, let's look at J here. J says, over what x intervals would the derivative be greater than 0? That means positive. So that's just asking where the slopes of the tangent line is positive. Well, the slopes of the tangent lines are positive anywhere this function's increasing. So over here where it's increasing, that's where the derivatives are going to have positive tangent lines. So question J and question F are talking about the same situation. So it's going to be that same interval going on there. And we're going to talk about this graph and its derivative in a little bit more detail. I just wanted to try to connect the idea that if you're given the first derivative graph, if you're given the original function graph, I'm given f of x, it's the original function, I can read the derivatives from that graph. At least as much as is the derivative negative, is the derivative positive, is the derivative 0. I can get that information from this graph of the original function just by looking at the tangent lines. By looking at the slopes of the tangent lines, I can get a general idea. I won't get an exact number except for 0, right? But I can get an idea. When I do a calculation for derivative, should it be negative in this area? Should my calculation for derivative come out positive? You can get all that from the graph here. Okay, so deep breaths, we got this. We're going to look at this graph in a little bit more detail, and we're going to connect it to the idea of sign charts. The idea of sign charts. Okay, so here we go. Same graph, but we're going to do some calculus here. We're going to create what we call sign charts. Okay, so sign charts are just a visual. They're kind of like a diagram. It's a chart. It's a visual that organizes information for us. And you can do a sign chart for a regular everyday function. You can do a sign chart for a derivative. So we're going to create sign charts here. So A is asking us to create a sign chart for the first derivative, or for f prime, right? For the derivative. Okay, well, here's our function. Just take the derivative of it. And when you're taking the derivative, you can just keep in mind that x is the input variable. So if you're taking the derivative of x, it's just going to be a plain everyday 1. So you don't really need the chain rule when you're taking the derivative of this function. You can do it if you want, but you don't need it. So let's go ahead and take the derivative real quick. So x squared is going to be 2x, technically times the derivative of the base, which is 1. And minus 4x is going to become minus 4. And the derivative of 3 is going to be a 0, so we don't have to write that. And just heads up, keep in mind, as we're doing this, that if your original function's quadratic, then the derivative is going to be 1 degree less than that, right? Because our power rule says we drop it down a degree. So if my original function's quadratic, my derivative's linear. Okay, what in the world is a sign chart? How are we going to create a sign chart for this? Okay, so this is how we create a sign chart. We need something called a partition number. So partitions are what breaks something up, like partitions break up a room or partitions break up a road. So a partition number breaks up the number line, right? So we need what we call partition numbers. Okay, and partition numbers are where the original, are where whatever you're looking at, in this case we're looking at our derivative, where our derivative would be either equal to 0 or where our derivative would be undefined. And I know we kind of skimmed over sign charts back on test 1. I ended up not testing them because of all those technology issues we had. We kind of skimmed over them. But the reason why these are partition numbers are this. Sign charts are going to deal with signs, negatives and positives, right? Well, the only way you can change from positive numbers to negative numbers is if you cross through the number 0, right? That's the only way you can do it. And same, if I want to go from negative numbers to positive numbers, I have to cross through the number 0. So 0 is like a threshold or a boundary between positive and negative numbers. And for sign charts, we're going to care about where are outputs positive, where are the outputs negative. So that 0 is going to be a possible divider between positive and negative. It might not. You might have a case, you remember from algebra, where you have a graph that bounces off, it hits 0, but you're going to have positive outputs on one side, it's going to hit 0, and you'll have positive outputs on the other side. So having a partition number doesn't guarantee your signs are going to change from positive to negative. It just means there's a chance they might. So we put them on this sign chart to help separate positives from negatives, or potentially separate positives from negatives. And same thing can happen with numbers that are undefined. With undefined numbers, you know, if we had something like a rational, you could have an asymptote that could create different outputs and inputs. So they're just numbers that like could possibly split up positive outputs from negative outputs. Okay, so let's figure out where this derivative would be 0. So I need to set the derivative equal to 0. It's a polynomial, so it's always defined. So I don't have to worry about that one. And do y'all want to know the super amazing good news? Since they changed this class from 4 credit hours to 3 credit hours, we only graph polynomial functions. Isn't that exciting? We used to do rational functions and all these other, you know, log functions. We just do polynomials now. So it's going to be nice and pretty in here. Nothing too awful. But okay, so let's go ahead and set this to 0. Where would this be equal to 0? So this is just straight up algebra. What x value would I plug in here to make this rule equal 0? We just solved that for x here. So if 2x equals to 4, divide by 2, then x would be a 2, right? So I'm going to put that number. So the way the sign chart works is this is your x-axis. It's this x-axis right here. And my partition is this little line, and that's happening when x is a 2. And this sign chart is describing derivatives. So above it, I would say if I put a 2 into the derivative, I'm going to get a 0 out. So at that partition, if I put a 2 into the derivative, I'm going to get a 0 out. So now we have to figure out what's happening in other areas. Oh, and let's go connect that over here to our chart. Is it true that when x is a 2, right here, when x is a 2, is it true that the derivative would be 0 there? Would the tangent line have a 0 slope? Yep. So we're just translating information like from this function or from the graph to a sign chart. We're just organizing it in a different way. Okay, so what would we predict the derivative should be to the left of that point? Remember from our graph, we saw that our derivatives, our tangent line should be pointing down. I would predict that I should get negative outputs for any x value to the left of that partition number, but we're just going to test it. These are called test points. So let's go ahead and test it. Pick any number there. I don't know. You want to pick 3? Doesn't matter. Let's pick x equals 3. And I'm going to put 3 into the derivative because this is a sign chart of the derivative. So I'm going to put 3 in there. So I go to my derivative rule. The derivative rule says 2 times the input minus 4. Hold the phone. 3 is not to the left. 2, y'all. Oh my goodness. 3 is bigger than 2. Let's try 1. 1 is to the left of 2. Okay, nothing to see here. Nothing to see here. Okay, 1 is to the left of 2. 1 is less than 2. So let's go ahead and plug that in. Okay, so 2 minus 4. 2 minus 4 is negative 2. So see how this output is negative? That's all we care about here. So I would put negatives on that sign chart. And since this is a polynomial and it's continuous and there's no jumps or asymptotes or anything, that's telling me that anywhere to the left, any input I pick that's less than 2, I could pick 0. I could pick 1.8. I could pick negative 20. Like any input I pick, if I put it into the derivative, it'll give me a negative output because the derivative is going to be negative in that region. Okay, so just since I messed that up, let's give me a status. After I fixed the number, are y'all kind of, give me a status. How do you feel about the fact that I picked 1 eventually, and I'm putting it in the derivative to describe what's happening to the derivative, and I'm just recording that information in a chart? Like, I don't even know yet. Okay, let's keep going. At any time, feel free to interrupt me, raise your hands, just ask a question out loud. I promise if you have a question, other people do too. Okay, so now we're just going to complete our sign chart. So now I have to pick a number bigger than 2. That would be 3. Okay. So I'm going to input 3 into my derivative rule. Remember, it's sign chart of the derivative, so I'm putting in my derivative rule. So I'm going to put a 3 in there. That would be 2 times the input minus 4. That would be, yeah, that would be 6 minus 4, which is a 2. That would be positive. So every input in that region would create a positive output. And I can see that over here in on my graph. Because what's going to happen, just so you know where we're headed with this, in a minute, I'm going to give you only the sign charts. And from the sign charts, you're going to have to create a graph. Okay? We're working our way up to that point. Right now, I'm giving you an equation or a function, and you're creating a sign chart and connecting it to a graph. You're trying to make connections. But where we're headed is I'm going to give you only sign charts. And from the information given in the sign chart, you're going to have to translate it to a graph. And Desmos is not allowed on test 3, just heads up. No Desmos on test 3. On the homework, you can use Desmos to check yourself, to help you learn, but you cannot use it on test 3. Okay. So there's a question in the chat about the numbers. Let me come over here real quick. So we have to pick numbers less than. Okay, so the way you pick your numbers, Jocelyn, is you look at the partition number. And then, so my partition number was 2. So I just had to pick a number less than 2. And then I had to pick a number on this side bigger than 2. So greater than 2. That's how I knew how to pick. And you can pick any number less than 2. I happened to pick the number 1, but I could have picked 1.5. I could have picked negative 10. You know, and then I can pick any number greater than 2. 2 is just that partition number. Since when x is 2, the output was 0, there's a possibility I could go from positive to negative if I cross through the number 0. And in this case, I did. I changed from negatives to the left of 0, and then I changed to positives to the right of 0. Sometimes you'll see a sign chart that looks like this, where it's going to be negative on the left and negative on the right, and that's okay too. Or it could be positive on the left and positive on the right. That's okay too. But if you're going to go from negatives to positives, the only way that can happen is if you cross through 0. That's why 0 is an important number to put on a sign chart, because there's the potential to change signs. And if you're changing signs, your rate of change is going from decreasing to increasing. And that's going to tell us a lot about what's happening to a profit function or to a revenue function later on. We're working our way up to that. How do you feel about that, Jocelyn? Oh, okay. She said, okay, got it. Cool, cool, cool. Okay. So, before we move on to second derivatives, I want to do something here. I want to graph my derivative function. So I'm just doing this on the fly here. So I want to graph below here. I want to graph the derivative. So the derivative was linear. We should all be able to graph a line, right? I'm going to graph that, but I'm going to sketch it. Well, let's see. I'm going to sketch it down here. Little trip. You could use Desmos to help you remember how to do this. But remember, your y-intercept is going to be -4. And your slope is going to be 2. So I'm going to come down here to -4. And then my slope is going to be up to over 1. Up to over 1. up to over 1. Okay, I'm going to get a little graph here. And this is a graph of my derivative here. This is a graph of my derivative. So when I look at the graph of the derivative, is that just like teeny tiny on your screen? Let me go see. It's kind of, okay. So when I look at the graph of the derivative, what information can I get off of this? Well, let's just take a look here. Let's take a little look for a second. One important point I can get off of this graph is here. This point is telling me that f prime at 2 is going to have an output of 0. Remember, this is the graph of f prime. So if I put the input 2, the x value 2, into the f prime graph, the height or the output is 0. And then if I look over here to the left, see how all those outputs are negative? Those negative outputs are corresponding to this part of the original graph that had negative rates of change on the original graph. A negative rate of change on the original graph is corresponding to negative outputs on the derivative graph. And positive rates of change on the original graph are connecting to positive rates of change on the derivative graph. So we're going to start working our way up to making these connections a little bit stronger, but I thought I would trickle it in here since this is like we can kind of visualize what a linear derivative would look like. It's a line. We're going to start making these connections between graphs. So reading our graphs really slowly, but we'll work our way up to that. So this first derivative sign chart, it's telling us about the tangent lines. It's telling us about rates of change. That's information we get from first derivatives. Okay, so technically there is nothing new in the calculus so far, except we had to really revisit sign charts because we kind of skimmed over that on test 1. But now we are going to talk about a brand new idea. We're going to talk about the idea of a second derivative. Okay, a second derivative. Oh, sorry, I heard a little chime. What is the blue color? Okay, so hold on real quick. Yes, sorry, oh, there it goes. Okay. So the light blue color there, if I look at my light blue color that I've highlighted, this point, oops, hold on real quick. It's not writing. Okay, right here. This point right here on my graph. Okay, this point tells me two things. If I'm looking at the original graph, just f, if I put 2 into the f function, the output is -1. But if I put 2 into the derivative function, the derivative or the slope of the tangent line is 0, right? So I was trying to show that this point on the original graph, I can read from that minimum value that the derivative would be 0. If I look at the derivative graph over here, the derivative graph crosses the x-axis at x equals 2 because the derivative, the output on that graph, when x is a 2 on the derivative graph, the output is 0. I was just trying to make the connection that I can read this information about the derivative from a original function graph, or I can read it from the graph of the line. It looks different, but it's the same information. It's just one time I got the f prime information from the original graph because I was reading tangent lines, and one time I got that f prime information from the graph of f prime itself. And if that's still super confusing, we're going to get into it in more detail. I just thought I was going to sprinkle that in to plant a seed, but if that seed's not growing yet, that's okay. I might have gotten a little ahead of myself. Okay, so let's talk about this new idea here. This new idea of f double prime. Dun, dun, dun. Let's look at that. F double prime. We call this a second derivative. A second derivative. that means you take the derivative of the derivative. So it's the derivative of the first derivative. So f prime, we're now going to call that the first derivative. And f double prime will be called the second derivative. It's just the derivative of the derivative. So the derivative is the rate of change. So its derivative is how the rate of change is changing. But that's going to tell us things in business context. Is my rate of change increasing? Is my rate of change decreasing? Am I losing money faster? Am I losing money slower? Like what's happening here? So that's all going to be tied into this idea of second derivative. But we're just going to start from scratch. We're just going to find it. So we're going to start with our first derivative and take its derivative. Well, the first derivative was linear. You can see it's in the mx plus b format. So the slope is 2, so the derivative should just be 2, right? And keep in mind that x is the variable. So if you were doing chain rule, x prime would just be a 1, so you don't really need it. So the derivative of 2x is 2, and the derivative of the constant 4 is 0, so we don't need to write that. So the second derivative is a constant. It's always going to be a 2. It's always going to be a 2. What in the world is that telling us? Well, you might be asked on my math lab to create a sign chart for this. We're starting with a really basic problem. So the sign chart for this is almost kind of weird or silly. But if f double prime is constantly 2, then it's never going to be 0. So we don't have any partition numbers on here. Remember how to read a constant function. That means any input I pick. So let's say I tried to put a 0 here. If I put a 0 into this function, the output's still 2, so it's still positive. If I put a, let's try -1. If I put a -1 into this function, the output's still 2, so it's still positive. See how it doesn't matter what I input here? It's a constant function. If I put a 5 in there, the output's still 2, so it's still positive. So you would get a sign chart with just always positive. You wouldn't have any partition numbers. The function I'm looking at is the second derivative function. It's never going to be 0. It's never going to be undefined. It's always going to be an output that's positive. So your sign chart would look like this. So what in the world is this telling me about my original graph? So I'm going to come back up here to this original graph. What in the world is it telling me? Well, we're going to learn that the second derivative tells us about the shape of the graph. So f double prime tells us the shape of the f of x graph, the original graph. Tells us the shape of the original graph. So the shape of this graph, this shape up here, I know this is going to sound weird, but this shape, this U-shaped graph, we're going to call that concave up. So let me write that down. Concave up. We say this graph is concave up. It's a U that's opening up. If your second derivative is positive, you know you're going to have a U-shaped graph that's opening up. Concave up. So let me come write that down over here by my chart. So the shape, this tells us, so if f double prime is positive, the shape of the original graph of f of x is what we call concave up. Concave up. I'm going to write CC up probably for concave up because I don't want to write concave up. But a concave up graph just looks like this. It's either a U-shaped graph or it can be part of that. It can look like that or it can look like this. Anything with this general shape. This is concave up. This is concave up. This is concave up. All of those are concave up. So this is just new vocabulary. You're not really connecting the dots to any algebra here. This is new calculus vocab. This shape is called concave up. If it's concave up, you're going to know the second derivative is positive. You're going to learn that. You're going to make some connections with that. Right now, we're just laying the foundation. And something else this second derivative tells us, remember, the second derivative came from the first derivative, right? So I'm going to plant a little seed here. And again, if this goes over your head right now, it's okay. But if the second derivative is coming from the first derivative, then the second derivative tells us how the first derivative is changing, right? Because derivatives are rates of change. Derivatives are rates of change. So the second derivative would tell me how the first derivative changes. And if the second derivative is always positive, remember that graph of the first derivative I drew over here? See how the tangent lines on that one are always positive? They're always going up. Remember that derivatives are tangent lines. So if I have a first derivative graph, its tangent lines are its derivative. So if I have a first derivative graph, the tangent lines on the first derivative graph are describing the second derivative, the derivative of that graph. So all these lines are telling me the second derivative is going up. The second derivative is going up. The second derivative is positive. Sorry, not going. The second derivative is pointing up, so it's positive. And isn't that what the sign chart is telling me here? So deep breaths, there's a reason why we're doing this over 2 days. I'm trying to plant a lot of seeds today so you can think about it over the weekends, and then we're going to start wrapping things up and connecting things next week, okay? So I know it's a lot, but just always ask yourself, what is a derivative telling me? Well, on a graph, a derivative is tangent lines, right? In a word problem, a derivative is a rate of change. So if you just keep that in mind, that basic idea that on a graph, a derivative is describing tangent lines. In a word problem, a derivative is describing a rate of change. And then just be careful what graph you're reading. If I'm reading an original graph, the tangent lines are the first derivative. If I'm reading a first derivative graph, the tangent lines are the second derivative. Like, you just have to start sorting everything out in your brain. Okay, and we're going to talk about this some more, so don't worry about it. So deep breaths, we're just planting seeds. So we've seen concave up. What is concave down, right? So let's talk about concave down. I'm going to show you a concave down example. Okay, this graph right here, it's a quadratic. It's still U-shaped. We're keeping it really basic quadratics. Everyone should be comfortable with quadratics from algebra. But see how the U's pointed down? This is concave down. Concave down. So concave down. So let's see the sign charts to confirm that this is concave down. So I have the function value there. Let's do the first derivative sign chart. Let's do the second derivative sign chart. Let's connect the ideas there. Okay, so first derivative. Again, my input is just a plain old x, so that means the derivative of x will be a 1, so we don't need the chain rule. So let's go ahead and find our first derivative. So the derivative of 4x will just be 4, minus the derivative of x squared will be 2x. Okay, let's find our partition number. Where would this be a 0? Or undefined, but it's a polynomial, so we don't have to worry about it, right? So let's go ahead and solve that. Okay, so again, our partition number is 2 here. X equals 2. And we're describing the first derivative on the sign chart. So I'm putting 2 into the first derivative, and I get a height of 0. And can I confirm that on my graph, since I'm lucky enough to have the graph given to me? Let's confirm that on our graph. Locate x equals 2 on the number line, go up to the ordered pair, and see, does the derivative really equal 0 there? So here's x equals 2 on my number line. I go up. Here's the point on my graph. Right? So here's the point of my graph. In my function, if I put 2 into the function, it has a height of 4, right? If I put 2 into the function, it's a height of 4. But if I put 2 into the derivative, it has a horizontal tangent line. So see how the derivative would be 0 there? Just like my partition number told me. Okay. So now let's just confirm some positive and negative outputs here. So I'm going to pick any number less than 2. So I'm going to pick, I don't know, let's pick 0 this time. 0 is a fun one. That's easy to plug in. I can't mess that up. And I'm plugging it into the derivative. So the rule for the derivative rule, not the function rule, is 4 minus 2 times the input. So the derivative would be 4, which is a positive number. I don't really care about the actual output value. I just care is it positive or negative. In this case, it's positive. And that's confirmed, right? Here's 0. See how the tangent line's positive there? The derivative. So if I put 0 into the function, it's 0. But if I put 0 into the derivative, it's a positive 4. The tangent line's positive. And the tangent line's positive everywhere until I hit that maximum point up there. So all this region would be positive. All this part of the graph, all this part of the graph would be positive. Okay, let's see. Is it 4 or 2? So for what I just did right there, I was focusing in on an input of 0. So my input was 0. And I put 0 into the first derivative. And when I did that, the output was 4, but I just care that it's a positive. I don't really care that the output's 4. I mean, I put that here on my graph. If I input the x equals 0 into my original function, it's a height of 0. But if I put x equals 0 into the derivative, it's a 4. All we care about for this sign chart is that 4 is a positive number. So I described everything in this region as positive. Oh, go ahead. Oh, it's 2 times 0. The derivative rule. I just followed the derivative rule up there. Oh, I see. Okay, let me make that a little bit more clear. Thank you. I see where it's coming from now. Okay, so that was 4 minus 0, which is 4. And that came out to be positive. Thank you. Cool. Awesome. Thank you for that. Okay, so let's go ahead and confirm on the other side. I'll just pick any number here. I don't know. Let's pick 3 again. And again, I'm going to put that into my derivative rule. So my derivative rule up here is 4 minus 2 times the input. So that would be 4 minus 6. So that would be negative 2. So all I care is that it's a negative output. So that's going to tell me anywhere in this region is negative. So anywhere over here, I should have a negative tangent line. And we can just confirm that real quick. So I'm going to locate x equals 3. Here it is. I'm going to locate that on my graph up here. So if I put 3 into the original function, the height is 3. But if I put 3 into the derivative, I got a negative 2, which makes sense because the tangent line's pointing down there. So show me a status how you're feeling about that first derivative sign chart now. Show me a status. How are you feeling about that first derivative sign chart? Okay, cool. So now let's do our second derivative. Derivative of the derivative, and we've looked at our shape. Since we were given the graph, we know it's concave down, right? So we know we probably can make a guess on what we should be getting here. But let's just go ahead and find it real quick. So here's my first derivative. I'm taking its derivative. So the derivative of 4 is a 0. The derivative of minus 2x is minus 2. So the second derivative is constant again. It's negative 2. That means no matter what input I pick on this number line, doesn't matter what I pick, the output's always going to be negative. And if the output was positive, we called it concave up. Now the output's negative. We're calling it concave down. So I'm going to put on here, if f double prime is negative, the shape of the graph is concave down, of the f of x graph. That's going to be concave down. And remember, f double prime is describing the first derivative. And if I look at this first derivative graph here, if I graphed that, you type it into Desmos or something. If I graphed the first derivative, I would start at 4 and then have a negative slope. This would be the graph of that line right there. And see how the tangent lines there would always be negative? That's just the tangent lines of the first derivative graph are the second derivative. The tangent lines of the first derivative graph are the second derivative. Okay, we're going to try to put all these ideas together in a problem. That might be where we end for today, but we're going to try to connect these ideas, like what in the world is happening here, with a function that's not quadratic. We're going to kick it up a notch, look at a cubic function. So let's see. So this might be where you start finally realizing, like, oh, now I know what question to ask. When I do something in a minute and you have no idea what I'm doing, it might help you know what question to ask, okay? So, so those partition numbers that I was talking about, where the first derivative equals 0, this is just more vocab real quick. So the partition numbers where f is equal to 0 or it doesn't exist, but we have polynomials, so we don't have to worry about that. Those have a special name. They're called critical values. So where the first derivative is 0, where you have a chance to change your slopes of the tangent lines from negative to positive or positive to negative, that's called a critical point. Okay, and I have some more information there that we'll talk about. Okay. And then where the second derivative is going to be 0 is going to be called inflection points, and I'll talk about this. So if we're talking about second derivatives, it's just going to have, or does not exist, but again, we have polynomials, we don't have to worry about it. Those are going to be called inflection points. So these are just some vocab words that are going to come out, and we're going to say them over and over again the entire chapter, so they'll sink in. I just wanted to start using them now that we kind of have a little bit of practice with sign charts under our belt. Okay, critical values and just heads up, since we have polynomials, again, we don't have to worry about this, but critical values and points of inflection have to be in the domain of the function. But if we're dealing with polynomials, the domain is all real numbers. There's no asymptotes, there's no holes or anything. So we don't have to be so worried. So for those of y'all, I know some of y'all have had calculus before. In a trig-based calculus class, I know there's like a lot of rules you have to go over for critical points and inflection points. We don't have to go over all those rules because we're just going to be looking at polynomials in this chapter. So deep breaths. Okay, so here is a cubic function. Here's a cubic function. And what I want to do here, I'm going to add some instructions. We're going to create an f prime sign chart and an f double prime sign chart. We're going to create those. And then we're going to talk about these new vocab words, critical points and inflection points. We're going to talk about them. Okay, so let's take a look about this. I bet we could pick out important information without even doing the algebra. So just looking at this graph, where would the derivative be 0? So put it in the chat. What x values? Remember, you're picking x values. What x values on this graph would create a first derivative of 0? Drop them in the chat. What do you think? Yeah, 0 and 2. That's right. 0 and 2. When I look at this graph, if I look at tangent lines, see how my tangent lines are going up, 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 but then they start to level off. And then I get to this point and my tangent line goes horizontal. So that point right there where x is 0, what do I know about? I'm going to write this down. So if f is 0 in the original function, it's a height of 5. But if I put it into my derivative, I should get a 0 because see how my tangent line flattens out? And then my tangent lines are negative for a while. But then it levels off again right here and hits 0 again. So let's write down information we know about that. So that's happening when x is 2. So when x is a 2, if I put 2 into the original function, it's located at a height of 3. But if I put 2 into the derivative of the function, then that would be a 0 because there's a horizontal tangent line there. And then the tangent lines start back up positive again. So we're going to just confirm that with the algebra. We're going to confirm that when x is 0 and x equals 2, the first derivative should be 0. So let's go ahead and do that. Let's take our derivative. So here's the original function. I'm just going to rewrite it. And we're just going to take the derivative of it. So my original function was 0.5x cubed minus 1.5x squared plus 5. Okay, so let's go ahead and take the derivative of that. Just doing my power rule here. So that would be 1.5 x squared minus 3x plus 0, but we don't have to write that. Okay. Well, I got to set that equal to 0. So now I want to know for what values of x would this be a 0? It's a quadratic derivative, right? So you could do quadratic formula, but I'm just going to factor out a GCF. So we kind of did this back on test 1 and again on test 2, the idea of if I factor out a GCF so they have an x in common, that'll leave me with a 1.5x minus 3. This is just algebra. Once I factor out the GCF, then I can use my 0 product principle. So either x equals 0, and wasn't that one of my x values that I got? That would create a derivative of 0. So if I put x into the derivative, I'm going to get a 0. And then according to the 0 product principle, the other factor could also be 0. So I would add the 3 to both sides. Divide by 1.5. And I get x is 2. Wasn't that my other x value there? So if I put a 2 into the derivative, I'm going to get a 0 out. And if I wanted to create the first derivative sign chart, this is what it would look like. So 0 and 2 are my critical values. The critical values that make my first derivative equal 0. That's 0 and 2. That's that new vocab word. We call the first derivative equal to 0, those x values that create that, we call those our critical values. So I'm going to put those, I'm going to create a sign chart here. So if I wanted to create a sign chart, I draw an x-axis. This is a sign chart for f prime of x, so I'm going to label the sign chart f prime of x, and I put that above the x-axis because the output descriptions go above the number line. Then I just put those 2 points there, 0 and 2 are my x values. And my MATLAB is just going to put zeros above that because the outputs would be 0 there. I like to put a little bit more information than that. So this is how it would look on my MATLAB. I like to write in that this is x equals to 0 and that this is the derivative when I put 0 into the derivative function. That's the output. I like to write this, but you don't have to. It just seems like the more information we can put on here, the easier it is to understand. And then to save us some time, instead of doing all the test points, because I know you can do the algebra, I'm just going to get the positive and negatives from my graph, and you can verify it over the weekend by doing some test points. But for example, if I tested x equals -1, if I tested this point, and I went up and I plugged it into my derivative, see how the tangent line would be pointing up? So that would be a positive output. So any x value that I pick to the left of 0 would create a positive output in the derivative function. And again, you'd be plugging that into the derivative function. I would put -1 into the derivative and I'd get a positive number out. And then if I picked a number between 0 and 2, so for example, if I pick the number 1, if I put 1 into my derivative, I should get a negative number out, because see how when I picked that, the tangent line there would be negative, so the calculation should be negative. And then after that point, like, if I picked the number 3, for example, if I put 3 into my derivative and I did the calculation, I should get a positive number out, because I can see here I'd get a positive tangent line. So I'd put positives everywhere there. So give me a status. How are you feeling about translating information from that graph onto a sign chart? Not too sure. Because remember, in a little while, what's going to happen is you're not going to be given this graph. You're only going to be given the sign chart, and you're going to have to create the graph. So we're trying to make connections by giving it all to you at the beginning, but then you're going to have to do it on your own there. So let's look at some of these important points here, just to kind of get our brain started. What's happening when x is 0? What's another, just in algebra, not in calculus, wasn't that a local max up there in algebra? So if I wasn't given this graph, if I was just given the sign chart, but I know my tangent lines are going up, they hit 0 and they come back down, see how I could deduce, just by looking at the sign chart, that there would be a local max when x is 0, because my tangent lines went from positive tangent lines to hitting 0 to being negative tangent lines. I could see that on my sign chart. I could see what the graph is supposed to look like just by looking at the sign chart. And same thing here. When x equals 2, when x was 2, right here, see how that's a local minimum? If I didn't have this graph, I could still see it was a local minimum just on the sign chart, because see how my tangent lines were negative? Then they hit 0 at 2, and then they went positive again, and that's creating that local min shape. And I could translate that shape to the graph. Just by looking at the sign chart, you can see those local mins and those local maxes by thinking about what would the tangent lines look when my derivatives are positive, tangent lines are going up. When my derivatives are 0, they horizontal out. When my derivatives are negative, the tangent lines go down. You can kind of start seeing the shape of the graph in the sign chart. That's where you're building your brain to head up to. Okay, so let's talk a little bit about second derivatives here. In hindsight, I maybe didn't give us a ton of space. But let's go ahead and talk about some second derivatives here. Let's look at the shape of the graph. Just looking at the shape, there's actually 2 shapes going on here. Are you ready? Let's look at our shapes. There's a shape going on here, this yellow region that's concave down. But then I flip over in this region. Oops. In this region, I start going concave up. So here I start going concave up. Where's that switch happening? At what x value does my shape change from this concave down shape, to the concave up? What x value is that happening at? Oh, careful. At 2, I have a minimum. Yeah, it's very, very subtle. It's actually, you're right, it's happening at 1. So these points, these special points have this vocabulary word up here. Point of inflection. So an inflection in someone's voice is like a subtle change, how the tone of their voice is changing. Or an inflection in music can be very subtle, like changes in how your vocal cords are working, right? So inflection points are super subtle, y'all. It's very subtle how I'm changing my shape here from a downward shape, and then it subtly changes to an upward shape right there when x is 1. Super, super subtle. So the algebra is going to show this. So if you're not seeing it right now, that's okay. The algebra is going to show it. But I think my inflection point, just looking at my graph, I think the inflection point is at x equals 1. But let's just see that. Let's find the second derivative. Let's set it equal to 0. And let's see if it really does happen when x is 1. So I'm going to take my derivative. My first derivative that we found earlier was this. It was 1.5x squared minus 3x. So we're just going to take the derivative of that. So the derivative of the first derivative is the second derivative. So x double prime. Let's just do our power rule. Okay, so that's going to be the derivative of 1.5x squared is 3x minus the derivative of 3x is just 3. And if I set that equal to 0, that's just algebra. You can factor a 3 out if you want, but it's just algebra. If 3x minus 3 equals 0, and I do the algebra there, see how my inflection point, if I put a 1 into the second derivative, I'm going to get a 0, so it's going to be an inflection point. That's where my concavity is going to change. So I'm going to create that sign chart really quickly in 1 minute. And we're just going to see this second derivative sign chart going on here. Oops. Shrink this up. It'll just take 1 second. So let's do a super quick sign chart. Okay. So my second derivative sign chart would look like this. I'm going to label it f double prime. My only inflection point is when x is a 1. I'm plugging it into the second derivative. So you'll have to verify this weekend, but if I pick a test point to the left of 1, so for example, if x equals 0, see how this shape is concave down in that area? So I would expect to get negative values out, and I'm going to do that really quickly. I'm going to put 0 into the second derivative rule. My second derivative rule was 3 times the input minus 3. Well, that's just going to be 0 minus 3, which is negative, right? So see how I get negative values? And that tells me my shape is concave down. And then if I pick another number like x equals 2, and I put that into the second derivative, that would be 3 times 2 minus 3. That'd be 6 minus 3. That'd be a positive number. So positive values anywhere there will be concave up. Okay. I know that's a lot. So what I'm going to do for this weekend, right now after class, I'm going to create a MyMathLab homework part 1. I don't think I've posted it yet. I hope I didn't. I'm going to put problems I think you should be able to do just reading graphs and connecting it to sign charts, reading sign charts and connecting it to graphs. If you're trying the homework this weekend and you're really struggling, that's okay because we're going to continue this on Tuesday. But then spend this weekend redoing these notes from scratch, rewatching this video as many times as you need to get the algebra down, how to read the f of x notation, how to read the f prime notation, how to read the f double prime notation. Keeping organized, like that's what you should spend your weekend doing, because you have to have a solid foundation on what we did today to be able to build on it on Tuesday. Okay? So deep breaths. Also keep an eye out for tests getting graded. Hopefully tomorrow night sometime, because I want these done as much as y'all do. So deep breaths. Y'all are free to go. I'll hang around if you have any questions.